So for people on the live stream, this is another internal design review meeting for the upcoming version of Wolfram Language. This particular one is about interesting new calculus functionality. Calculus not being a finished area even after all these years. So looks like we are primarily dealing with asymptotics. Is that right? Oh, we also have the elementary algebra stuff. Oh, cool. Okay, fine. All right. These are going to be two very different pieces. Okay, let's talk about asymptotics. So can I run some of this stuff?
Yeah, in external.
Okay, should I go to the documentation page?
Yeah.
Oh, my documentation thing is broken here. Doesn't open that. Okay. Asymptotic integrate. Is it? I mean, there's no meaning to, I mean, like asymptotic solve or something like this. Why isn't there a meaning? That's some kind of limit combined with solve or something. Is that right? Or is that?
You get, what you get is an asymptotic approximation to the solutions.
Yeah, it's more like series solutions. So asymptotic desolve value, you can think very much as, power series solutions, differential equations.
So why isn't this called series integrate?
Because series, some people think that series is something like Fourier series, which are not asymptotic.
Well, I understand, but this is returning a series, right?
No, it does not return a series. So we want these to be experimental now because we want to maintain the option of changing the output at some future date.
But so, wait a minute. So this is...
So one of the fundamental problems is the limitations of series. You know, and there might be fundamental problems. We just don't fully understand those problems yet.
Okay, but so let me understand this. So this is the integral of e to the t times x with t. I don't understand this.
You integrate from 0 to 1, but you view x as a parameter. You want to expand it around 0. Do you read the use case? Read the usage message.
Yeah, I did.
Okay, so is it still not clear?
I'm sure I did. Okay, so the indefinite integral here. So I should be able to do the indefinite integral here.
Yeah.
Okay. So the trivial case is something like,
I mean,
one. Why didn't that work?
You need to have, in the indefinite case, then it's t that,
Oh, why didn't that work with just a single one then?
Because there's no x in there, I think.
So what?
Well, that's a good point, but realistically, what you were asking for is to vary t around some,
Okay, so it's just a bug that one doesn't work.
I think so. But
okay,
but
what it slightly worked is just t. Is that correct?
Sorry.
If it did work, if one did work, it would just give t, something independent of x.
Correct.
Yeah, but you yes, but you have the x is the one you specify the expansion point around.
No, I understand.
Okay.
So if I compare that with integrate, okay, and then I say series of that x07.
That may or may not give the same.
And under what circumstances won't it give the same?
If there is no series, for instance, series can't represent it. If a different asymptotic scale has been chosen.
Okay, so in particular, then if what I do here is I say square root of arctan. Okay. Okay, that may not even be an integral that we can do.
Yeah, and there are simple things like x to the x.
Yeah, I understand. I don't understand why it's called asymptotic. I mean, I'm doing it around the point 0 here. I mean, asymptotic is usually, at infinity or some such other thing.
No, asymptotic at any point. Not at all.
Okay. Why isn't this called integrate series or series integrate?
Right. It's right, because we're not necessarily guaranteeing any sort of convergence. Right. So this
Why
is
does series?
asymptotic, like
Yeah.
in the way that QED expansions are asymptotic. They reach the minimum point and are useful, but they don't actually converge.
Okay, fine. But isn't that the case? Series also, if you do series on something with an essential singularity, for example. Okay, that's interesting. How did series manage to get a result there?
Because it doesn't use integrate.
Well, it differentiated the integral, right?
I see. So it treated that as a formal object and did the
Exactly.
differentiation.
Yes.
Okay. But so show me an example. So if I have something with an essential singularity, for example, so for instance, let's say I have, sine 1 over x or something. Let's do something like that. Okay, so now if I say integrate that thing over t, I'll presumably get a result. Okay, so now explain this to me. I'm going a series here. Maybe this isn't the relevant one to do a series with respect. Oh my gosh.
We need to do assumptions over there.
Okay, so what assumptions do I need?
X greater than 0 might be good enough.
Well, that's sort of interesting because that's a different result.
You have a constant of integration which might affect the result.
No, but I've got a log x term there.
Well.
No, I mean, this isn't bad. I'm simply trying to understand the difference between asymptotic integrate and series of integrate.
Sure.
And maybe this is an example where there is actually a difference.
Right, but don't forget that log of x is
0, and with respect to this, with respect to series expansion.
Well, the log of 1 over t is still a constant of integral. Well, log of 1 of them is good.
This is a log x times x. There's no is that a constant of integration there? It might log 1 over t sure isn't a constant of integration.
Log x.
No, that could be a constant of integration, but this isn't. Log 1 over t.
Yes.
But that is the same as this plus log x. That's the same as that term there.
Exactly.
Okay, so walk me through again. Why is asymptotic integrate not the same as series of integrate?
In the indefinite case, there can be a couple of reasons. One is a constant. An indefinite integral is only defined up to a constant.
Yes.
Okay, that's one potential.
Big deal. Okay, fine. I mean, we could have 16 different versions of integrate, which make different choices of constants.
That's right.
We've never been into that particularly because it doesn't really matter.
No, it doesn't really. Now, the other thing that can happen because of the solution methods, it might pick different base, asymptotic scale, if you like, to express the solution.
Just a minute.
Right, and I think maybe one sort of difference that's relatively easy to understand is that asymptotic integrate tries to give you about n terms, whereas series gives you quote unquote order n, whatever that means, which in some cases is fewer than n terms, and in other cases is more than n terms. And it's in some cases it's really quite mysterious what its meaning of n is, of order n is. So
yeah, that interpretation of what order means cannot stay. It just makes sort of sense. If you're in power series, it makes perfect sense. Okay, but the minute you sort of leave power series, it starts to be more and more vague. And when you get more complicated scales, it gets, it's like, who knows what it means? I have no idea what it means even. And the thing is that, essential singularity basically means not pole, right? And it's not that the poles and no singularities aren't interesting, but often the really interesting case is when you go beyond that.
Sorry, I spaced out for a minute. Could you go back and repeat this? So I'm trying to understand. Retry on this asymptotic integrate versus integrate thing versus series of integrate.
Most of the time, they will give very similar results. They should always be equivalent in some sense. Okay, if series can succeed, if integrate can succeed, etc., etc.
Okay.
But the essential property that asymptotic integrate guarantees is that you get a result that is asymptotic at the point that you specify.
And what does series guarantee?
I don't know. It's not clear what it guarantees.
Seems hard to guarantee. I mean, so you're saying that, I mean, this whole question about being asymptotic, isn't that really a nasty, complicated question in the world of essential singularities and all these kinds of weird things?
That's almost the only thing you have that you can guarantee. But yeah, it's not super simple.
But
I think that we will be able to.
Not like undecidable?
Well, I mean, it's all of our symbolic functions are undecidable. If you know, zero recognition is undecidable, so all of our symbolic functions are undecidable.
Okay, but let's. I'm a little bit confused here, but let's keep going because I think we're going to. This may be a little bit clearer. You know, when we talk about asymptotically greater than, let me understand that. So, I mean, for example, so can you give me an example? Let's take a look here of asymptotic greater.
I actually, if you want to pick one of them, I would pick asymptotic less because, or if you want to look at the illustrations, asymptotic less equal. Which one did you pick? Less.
Asymptotic less.
Okay. I think.
So what are these things being? Okay, xy goes to infinity. Great. Those are kind of trivial, but where are some that are non-trivial?
Well, the examples are not developed here yet. They're missing a bunch of examples, but I wanted to show you some applications.
Okay.
Okay, so if you can slow down because
yeah. Okay, go ahead.
So for instance, you can see the basic applications. They're sort of going to be intuition builders, as they often are. But then you can see here, there's a notion of approximation, absolute error. Small absolute error means that the difference is something that's going to have limit 0 as x goes to 0. Okay, and that's saying that it's asymptotically less, strictly less than a constant.
Yes.
Okay. And so you see a few examples there. They're not too many, but a few to get you that concept.
Okay, but these are all pretty trivial examples.
Yeah. How else can you learn?
No, I understand. But what are the non-trivial examples? I mean, are the ones with like series expansions? I mean, with like sums and so on?
Yes, you can go down to the, there should be something about asymptotic desolve and integrate both.
Yeah.
So.
Oh, where is that? Somewhere in here. Like if I go to combinatorics here, do I see non-trivial stuff?
They're not yet developed.
No, asymptotic approximation.
Yeah. Okay.
I mean, probably it's Roger's notebook, but I think it should be there.
Yeah.
Scroll down further. Should get some stuff over there. Yeah, scroll down further. Right. Now, I mean, now you start seeing some. Well, a little bit. Yeah. So if you go to.
Okay. So in this sense, what you're saying is, okay. So, but asymptotic equal doesn't have the same order thing that asymptotic integrate has. It's just saying, here are two functions. And is that the same as what isn't less Verogs? Oh, for goodness sake, not this stupid problem again. else do I do to fix this?
It is vararg. Asymptotic orders are undefined unless you specify at which point. And you
I
also need to
understand that
provide
point.
the
So
variable.
I understand that point. So I'm asking the question, okay.
Yes, less is
by the way,
vararg. Yes, it is.
okay, so this is a slightly weird design change here because asymptotic less is not a mirror of less.
It's an order. And there are more orders in the world than less.
Yeah, okay, but it has this x goes to infinity.
It needs to, yeah.
Okay, but in what sense is asymptotic? But asymptotic integrate has an order in a different sense of order. By the way, we've got a bunch of weird background noise.
No, it has an order in an asymptotic order. What you say is that whatever you sort of haven't given as an answer yet, you know, the rest, you know, if you kept on doing a higher and higher order, actually look at, instead of me saying it in words, look at the page for asymptotic integrate that explains what it is that it guarantees. Okay, you just scroll by it.
Yeah, but look, Roger, the thing that I'm concerned about is asymptotic integrate is a series-like function that specifies an order of expansion. Asymptotic
But
less.
order means order in the sense of this order, not order in the sense of polynomial degree.
What do you mean by that?
No,
What I mean
no,
is that
I think you're confusing asymptotic less and asymptotic integrate. Asymptotic integrate guarantees a particular number of terms.
no, it does not.
There don't seem to be 7 terms here.
No, it does not.
That's that looks like it's 7th order in X. Like the polynomial.
That just can't hold true. It's just the polynomial business just does not.
No, wait a second. This case here, it's to order 7 in polynomial orders, right? I mean, if I were to choose something here where I've got a very high degree, where X here is X to the 10th, right? I would see something fairly trivial. What the heck am I about to see here? Okay. I'm about to see that because even though I asked for 7th order and there just weren't any orders that could be gotten, yeah, there we go, right? I'm only getting that order because I don't have, there are no other orders. I'm only searching up to polynomial order X to the 7th. Am I making sense?
Yeah.
Okay, so I don't understand. What does that order actually mean? What does that number actually mean?
It basically,
go ahead. Yeah.
It's if you read the documentation, okay. Do you see the paragraph says if the exact result is G?
Yeah, and the asymptotic order is N. Then we have asymptotic series, asymptotic less.
Right. Now, if it so happens that the result is a sum, you know, so a series.
Yeah.
You know, to see the next paragraph there? To see below the illustration?
Yeah.
Okay.
So an asymptotic scale such that this is true. I see. So your point is there is a property, which is that, I don't understand this, that there's some asymptotic less and greater property that holds, given this order here. No, I'm really confused. I'm sorry. Can you, why do I have to state, so these things here are always Booleans. Is there ever an I don't know response from asymptotic less?
Yeah, it can give conditions on parameters and other things.
Okay, but it doesn't do that with an order.
I presume if you put an A in front of the X and the exponential, it'll give you a conditional expression.
Okay.
Which is probably the opposite of what it should do, but.
You mean it should give the
true and A, less than 1 or between -1 and 1 or whatever it is that it wants to be.
It's certainly false when A is greater than 1, but
Right.
more useful would be
You
to
don't know what it is for A less than 1. In fact, not.
If somebody's saying something, we can't hear you. Okay. I'm sorry. Let's do the following. Can we, just for the sake of the flow of this meeting, can we jump down to what I think are really straightforward things?
Sure.
And let's come back to this. I'm pretty seriously confused by this. And I'm seriously confused. I mean, you believe that the term asymptotic is used in the same way in asymptotic integrate as it is in asymptotic greater. Is that true?
Yeah.
And what you're not doing here is some kind of thing where it's just kind of like series is broken, so we're going to rebuild it. Or is that
we need a future extension of, hold on.
Yep.
That's spam calls.
So
here's the scenario around series. We've been doing some functionality is using the output of series. Series can only work for expressions. It can't work for solvers at this point, but we want it to eventually.
What do you mean by solvers? You mean implicit things like root?
Like an integrate or a solve or a desolve or things like that.
What do you mean it can't work for those? I mean, it
currently doesn't.
In what sense?
If I have an unevaluated solve, it seems to, an unevaluated solve, an unevaluated desolve, an unevaluated integrate, I should be able to get the series of that.
Right, which we noticed you could do back up here. Like right here, it did that.
So occasionally it might work.
Okay.
Okay. But it generally doesn't.
Okay, but it should.
It should. Okay. But here's the problem. The output of series has been the series data structure is designed to deal with power series, formal Laurent series, and formal Puso series.
But it was hacked to add
and really for the univariate case,
and for univariate only.
Right. So it needs to be extended. I mean, it was hacked to include essential singularity type stuff and so on, wasn't it?
That's right. Which means that you can't really, first of all, it can't represent things, so it represents things weirdly.
I understand. I agree. It's a 31-year-old structure.
Yes. Now,
I mean,
before we design a new series, we need to know what it needs to represent.
I agree.
Okay. Hence, we're building the solvers that will generate these series.
Okay. So just walk me through.
The other thing that's not clear, that the design of series of auto expanding when things come up inside, it's also not clear that that's going to be able to work for sufficiently general series.
Well, then we need something where it can, I mean, just like if you type in, 2 plus
What I'm
2.
saying is that we cannot have a new series right now.
No, I get it.
The scenarios need to
setting some outline, right? The analog of that is, x plus x simplifies, but some more complicated thing does not. So one would assume the same thing will happen with series. Just like here, we're effectively seeing that happening, right? We're seeing a fine Laurent series inside here, right? Mm-hmm. But the thing cannot resolve to a complete series because it doesn't know how to represent the essential singularity.
Right.
Correct? Okay, so then what we want to do, I guess, so I get your point, and I agree that, okay, so the goal then is to make certain experimental functions which are the beginnings of, by the way, do we think that in the sort of development post-Hardy fields and all this kind of thing, do we think there is a well-developed mathematical theory that would allow us in principle to represent these series, or do we think that the theory is undeveloped at this time?
It's a little bit of both, and we're proceeding to get to know and develop that as we speak. And this developing the solvers is part of that.
But in the univariate case,
in particular, the multivariate case needs substantial attention. Okay,
I understand,
and that leads pretty far but
Let me
it's
ask
going
a
to be
naive
very powerful.
question here. So when Hardy invented Hardy fields, he thought he was imitating orders of infinity in the Cantorian sense. I mean, he thought he was doing a transfinite number play, I believe.
I think what's turned out to be the case is those transfinite numbers have turned out to not be very useful for instance, infinitesimals and these hyperreals. So that's effectively not used there.
What is a hyperreal?
When you have infinitesimals or infinites,
Yep.
explicitly manipulable.
Yeah, no, I've heard of hyperreals, but how do they differ? So I mean, the Cantorian model was a particular model which included infinities and infinitesimals. You're saying there is a different model?
Yes.
Okay.
And Cantorian did not include infinitesimals.
No, I understand. He was only doing infinity. Right.
Right.
But so
but
my question.
Cantor thought he did that, but you know, in later development, it turned out he didn't.
Do what?
The infinitesimals. It was not sufficient.
But I mean, Cantor's original goal was some stuff to do with trigonometric series, if I'm not mistaken. I mean, he was trying to do something a bit like what we're trying to do here, except, you know, 130, 40 years ago.
Right.
But so just walk me through, though. Is there a systematic way? I mean, it just like there are orders of infinity and things like that. Are there similarly? Is that kind of the analog, like I think Hardy tried to do with Hardy fields, of these sort of orders of expansion and so on?
Yeah. Yes. So if you have, so what's reasonably well? I mean, we're mixing many things here, so I'm trying to answer constructively and more useful.
Yeah.
So one thing that you know and we know is that we need, in order to tackle essential singularities, or otherwise known as knot poles,
Okay.
we need to have a richer set of scales to express that in.
Yep.
Okay. And some of that is already built and inside, you know, Mathematica, Wolfram Language.
Mm-hmm.
And, you know, particularly in the new limit functions, make extensive use of that.
So do we have a symbolic representation of those new scales?
No.
And is that, I mean, is there an index? I mean, just like when you have an exponential scale, for example, is there some meaningful sense in which there is a numerical index that might be a transfinite number, but is there some numerical index for that, or is it just not thought of in that way?
It's not thought of in that way, because the see, if you predefined, I asked you, Stephen, if you're going to use this function, you need to tell me what scale you're going to use and then index into that.
Yeah.
You would have a close to 0 success rate.
Sure.
In using any of those functions, because you will guess the wrong scale every time. You know, at least, you know, except in the simple cases when the power scale and other things kind of work.
Well, I understand, but I mean, that's the question of what does that number mean, which we were discussing earlier. What does the 7 mean? Does it mean give me 7 non-zero terms? Does it mean go up to order x to the 7th, or what does it mean?
Well, I wish it could be terms, but the fact is that we can't always get a series. You can always get an asymptotic approximation, and often it is a series, in which case it could be terms, and that's a very well.
What else can it be other than a series? Just some blob of stuff?
So for instance, yeah, so just to give you an example, if you have just a linear differential equation, and you have an irregular singular point in that.
Yep.
Then what you're going to get is a prefactor of an exponential.
Yep.
That typically have a Laurent series inside of its argument there.
Okay.
Okay, that grows, and then you get the regular multiplied onto sort of a regular power series.
Yep.
That itself means it's no longer a series.
No, I understand.
In a fixed scale.
Right. Yes, this may or may not be useful, but I think one way to think about this is, right, just as you have multiple scales of infinities, right? You have the cardinal infinities, you have the ordinal infinities, and they may or may not be comparable. Sometimes they're comparable, sometimes they're not really comparable, right? this is order 7 in an appropriate scale, which may be some sort of log scale, exponential scale. So there are, our orders are always integers. We're not going, and this is give me order 7 in an appropriate scale.
I don't understand. If we have x to the pi, what scale, doesn't that give us yet another weird set of things going on?
Absolutely. But the asymptoticness and the number of sort of steps that you go down, that many steps, many times, is still well defined.
Okay, but
actually, you want to.
Yeah.
Sorry. No, I was just saying that you can go to asymptotic D-cell value and just look at regular singular points, because those already exploit. That's the next level up in scales. That just one step away from Laurent type. Sorry.
I'm typing into this. This is a disaster. Let me not do that. Asymptotic
D-cell value. Now,
okay.
Let's go down to scope examples.
Which one?
Regular singular points.
Regular singular points.
Okay. When you get the little, the simple cases first, but let's see. Let's get.
Oh gosh. By the way, somebody should report this bug. See that ghosted in X there? That's wrong.
Devendra, do we have any log powers here? I want to show things that are not just rational numbers.
Right. So there'll be some over there, but I think you might even get a richer set of examples for the WKB method. So if you go down to singular perturbation problems.
Well, you need some examples here that have log powers in them. I don't see any log powers.
Okay. Here. We could put in some,
So what are you saying? Singular perturbations?
So if you go to singular perturbations, right? You see the kind of answer you get over there from the WKB method. Yeah. So what's happening over there? Yeah, exactly.
Okay. So let me put this in here. Gosh, that X shouldn't be there. That multiplication sign shouldn't be there. I thought we went through this for this version. Oh my gosh, sigh.
I read a really good quote, which you will appreciate.
Yeah.
So asymptotic analysis is as confusing for the advanced student as calculus is for the freshman.
Lovely. Okay, so
but the thing is that we're going to make it elementary. That's our goal.
Is there any level at which it's not confusing?
Yeah, no, this will be, these asymptotic orders and all of these things will,
Are you sure? Are you sure it's doable? Are you sure that the math
yes.
just tangle everything up?
No, it'll work. It'll be great.
Okay.
This is a new powerful calculus that we're introducing, a third mode of computing.
What were the first two? Algebra and calculus?
Symbolic and numeric.
Oh, I see. Well, your claim is that this is approximate. This is like series tries to be, namely approximate symbolic computation.
Yes, exactly.
Right. But the notion of precision is unbelievably much more complicated in this case. And particularly for the multivariate stuff, I have no...
It's powerful magic.
Yeah. But it's magic that, unlike precision, which is parameterizable by a single number, for example, this is parameterizable. How do we think about parameterizing this? Is it parameterizing using some kind of collections of functions, or what kind of a thing would parameterize the level of precision?
This says, to first order approximation, you can still think of it as a series, and then it means the number of terms.
By the way, does this even have a hope if I give epsilon of 2 there? No. Why did that? So I see. So that then, wow, this is a complicated creature.
You can go quite a bit up. I could in probably 3 or 4 at least, maybe 5. I'm not sure, but yeah. So it's like an exponential of an asymptotic series.
Okay, with some extra hair here.
Well, because the initial conditions. If you remove the boundary conditions, you'll see the nicer structure.
If I just have no boundary conditions at all?
You should start seeing the structure there, actually, yes.
Okay, all right, fine.
It should be much nicer than.
Okay.
So now you see the
All right.
structure there. It's basically, and even the rational, the denominators might go away because they really are exponentials of logarithms, which got cancelled out.
I see. So that could be a log in the
Exactly. So the as logarithms drop out, you get these simpler structures emerging.
Okay. All right. But okay, this is still not completely helping me. So I mean, what you're saying is, I mean, one thing that's kind of annoying is that in the one case, in the case of asymptotic greater, asymptotic less, whatever, you've got something that looks like a limit going on. You know, x goes to 7 or something, or x goes to 0, right?
Right.
In the case of asymptotic integrate, you have something like that going on.
Well, actually, we could discuss that, okay? Because I think we should use the arrow notation here too.
Okay. Well, yeah, I mean, particularly if you don't even know what the orders mean. But right, I mean, this is, if you're saying asymptotic, I mean, that would make a lot more sense. Asymptotic integrate, asymptotic integrate of f of x and t, you know, the x integration, and then t goes to blah, blah, blah.
Exactly.
That's basically what you're talking about.
Yeah.
Except that what you want to do, in the case of the Booleans, there's no parameterization that you can give, presumably. Because
what do you mean by that?
Well, I mean, you can't say, look, it's either greater or it isn't. So
Yeah.
Right. So what do you do in the case where it doesn't know? What happens if I say asymptotic less? If I do a very trivial thing, if I say asymptotic less, you know, sine x 0, splarf. What does that mean?
Means that
not always less.
Yeah. It means that in the limit, you know.
Right. If you did that, besides the message, but if you just change that to, or if you, right. But if you, in your 0 example, if you change that to like 2 plus sine of x,
Yeah.
right, then it should give you.
True. I mean, it gives you a little false in this case.
Well, yeah. Oh, I'm a bit surprised by that.
Well, that's a bug. I
Yeah,
mean,
okay,
because
fine.
right now it's using a.
2 plus sine of x is clearly greater than 0. I was thinking the other order. 0.
Yeah, right.
Right. 0 and sine of x are not comparable because sine of x is always crossing 0.
Okay, so what I'm trying to ask is it's always the case that less or greater is a predicate that has a definite answer if you know it? Like, for instance, if I ask, you know, are the zeros of the zeta function, you know, I can formulate the Riemann hypothesis this way, right? And we don't know the answer to that at this time. So, or am I confused here? I mean, the Riemann hypothesis is just some version of this, is it not?
I mean, yes, it will be unevaluated in some cases. That's for sure.
Right, but what you don't get is this, well, it's right to a certain order, but not beyond that.
That's right. No.
Right. You just, right. I mean, and if you just think in terms of little o, f is either little o of g or it's not.
Yes. Okay, fair enough. So, right, but what isn't there a generic, I mean, forget integrate, isn't there just a generic, I mean, I'm really confused here. There's a 0th case of this, which is essentially asymptotic series in some sense, where you're just taking an expression and you're asking, just
That's
like
right.
series does.
Yes, there is.
Okay.
But for right now, we have series for that. Okay.
Okay.
But we don't know what the future extension of series.
No, I understand. But
Okay.
we also have limit, and limit. Okay, so limit attempts to just resolve what is the limit.
That's
but
right.
For example, in the case of sine 1 over x, as x goes to 0, limit is just going to say, I don't know what the limit is.
Well, no, it will tell you what the limit is.
It will tell you that the limit does not exist.
Yeah.
Okay.
This
fine.
one doesn't exist.
Okay.
That's correct.
Okay. But is there or is there not some approximation to that limit that does exist?
Yeah, well, I mean, first of all, when you use limits, you can use max limit, that exists, and min limit, that exists.
No, but I'm saying that this is the
No,
trade-off.
you're right, Stephen. Yes, you can have, you can even try series on it. I don't know what it will do, but
I think we just tried that. It just produces it just does that.
Yeah.
Right.
Yeah.
Okay.
But so one thing that's interesting with these asymptotics, if you prescribe a scale like a power scale, and you take a function like yours here, or e to the 1 over x at the origin. So in the power scale, that entire series is 0.
Yes.
Okay? What you're trying to express in a scale.
No, I'm aware, right? I mean, that's like for the particle physicists on this call, right? That's the whole business about instantons and non-perturbative solution.
Yeah. And physicists usually call these scales gauges, among other things.
Really?
Yeah.
No.
Gauge.
That was Weil called it that back in.
Oh, maybe it was Weil. Okay.
Yeah, I think not in the modern world. A gauge is something.
Yeah, it zoomed off in a completely different direction. Okay, but anyway, go ahead. But you're right. Yes, the e to the 1 over x thing is 0 in a standard expansion.
Yeah. But that doesn't mean we can't express it using asymptotics. We just need to use a different scale where it starts to register.
Yep. But okay, but so what you're saying is you have a limit, but then the wigglings around that limit, there's some expansion of stuff around that limit that can be represented as a series with respect to some scale.
That's right.
Okay. But so
and they really show up because they need it, for instance, to express the solutions of differential equations and integrals and etc.
No, I understand that. But so the trade-off here, the thing that's rather bizarre, is this asymptotic less being. So asymptotic less is limit-like, and asymptotic integrate is series-like.
That's right.
Because one of them is going to give a predicate with a Boolean answer, and the other one is giving some expression as the answer. Is that the idea?
Yeah. Because this allows you to sort of, and you often use this these asymptotic relations are used to express a number of things, and we've just made them computable.
Yeah, and I understand. What's the difference between asymptotic equal and asymptotic equivalent?
Equal is when it's both big O and big omega, otherwise known as big theta.
Okay, so what's an example of something which is asymptotically equal, asymptotically equivalent, but asymptotically equivalent is stronger than asymptotically equal, is that right?
That's right.
Right. I mean, x and 2x are asymptotically equivalent, but they're not asymptotically equal.
No, the other way around.
What other way around?
They're asymptotically equal.
Yes, but not asymptotic. Yes, I said that backwards.
Exactly.
But that is what I meant.
Yeah.
Okay. Okay. Interesting. All right. Let's keep going. We're going to loop back to this asymptotic stuff because it's difficult. Okay. So improved solvers. What is this?
Sorry about that. I meant to get that more clean. So there's been numerous improvements to these limit functions. It's
okay. Is this something we should look at? Does it change the design?
No.
Just more stuff.
No, I mean, I think that we have new examples, but that's about it.
All right, so let's look at our algebra stuff.
Just things that didn't work now work.
Adam, you are very hard to hear.
Okay, so we just have some new methods. So things that we couldn't do in version 11.2 we can do now, but there is no change in the design.
Okay. All right, let's take a look at these elementary algebra things for a minute, which we looked at. I mean, we looked at these a couple of years ago, didn't we? I mean, this is.
I don't know. I haven't been involved in that.
Yeah.
Who's reviewed this design?
Well, I did, and
Okay.
and I thought Roger had reviewed these.
No, I've done that too.
Right. Right,
Okay.
and there's so subtract sides and this divide sides have a one argument form. So, right, so if you subtract sides A,
Yeah, it's A minus B equals 0 or something.
right.
Okay. Have you tried really using these for something? That is, for example, if you want to give a derivation, has Chip Hurst looked at these?
I don't know if Chip has looked at these. I mean, the one thing I have in the documentation, probably under applications, a sort of a derivation of completing the square. Yeah, you'll just need to open the subgroup of applications. It's just
Of add sides?
Yeah. And you'll see that, you know, I need to, like, I think somewhere I need to
Let's copy it in here. So it's,
you know, I needed that extra expand at the end in order to make it right. So you see on the second line, after I multiply, it doesn't sort of multiply out the sides. I needed that extra expand.
wouldn't that be a good thing to have by default? Okay, so here's the little quadratic form thing. And wow, what is this? Assumptions.
Right, you're multiplying both sides of an equations by a you know, pure factor. So we need A to be not 0, otherwise we'd get a conditional expression.
Oh gosh.
And that
Really?
might actually be sort of worth reviewing. Or would we get, I think we'd get a piecewise expression.
Oh wow. Well, right there. I mean, since this is intended to be for sort of the elementary, why do we get this?
Well, actually,
Because if A is 0, then you've multiplied both sides of an equation by 0, and that's not defined.
I mean,
Why didn't the expand burrow its way into that conditional expression, but piecewise expression?
That's a question for Adam. I'm not sure.
It doesn't do that normally. That doesn't go into piecewise. Why? I mean, there is, other than it's not implemented this way. Yeah, it could.
It seems like it should. Roger, do you have any comments on that?
Sorry, could you repeat just which one?
Should expand burrow its way into piecewise expressions?
We have to very carefully look at that because that can tip over the whole system.
Right, and I guess the question is, does it burrow just into the, you know, equations or also the conditions?
Right. Another issue is if you have piecewise inside the larger expression, should it go inside the piecewise that's multiplied by x or something like that?
Okay, but if I might say so, this multiply sides is in the category of not terribly useful. I mean, this is, you know, we were trying to provide a function that will make it easier for people who are doing fairly elementary things. By the time it's zooming off into the piecewise world, you know, it's definitely not in the easier category.
Well, it's also pedagogic in the sense that it tells you if you want to multiply by something, you should make sure that it's not equal 0. So that's the kind of thing that students are taught, that, you know, they shouldn't just blindly multiply by something. There are conditions for that.
Yes. Fair enough. Okay.
Yeah, if you look at the multiply sides page, they're sort of different settings for generate conditions. Devendra and I felt that piecewise was less scary than conditional expression, so we decided so the default value is all, which is return all possible answers using piecewise. So, like, for example, if you divide an inequality by A, right, you'll have two different answers, one where it's you know, where it's reversed and one where it's not reversed.
So I guess my question would be, what for the typical student, at some level, generate conditions are automatic, which I would assume here, if I were to do this, would say, if I did that, and then I said generate conditions, what on earth is that? Generate conditions is, oh, great. That's, by the way, something to note, that's autocomplete thing is going to need to change for this function.
Right. Now,
Did you understand that point? Sorry, did you understand that point about the
yes.
Complete? Okay. Yes. Now what?
Now copy that input and change that quadratic to, b less than c.
This here?
Yep. As opposed with the default value, and now try that again without the setting generate conditions.
Okay.
So in that sense, it's giving you, certainly for inequalities, I think that's sort of a better and less scary looking answer.
Yeah, well, it's not helped by the fact the conditional expression doesn't format in a nice way. But, okay, so, gosh, okay. Well, let me just try to understand. Gosh, there I was thinking these functions were just completely trivial structural functions, but they're not. So what are the other gotchas in these functions?
So, I mean, apply sides is both simpler and a bit of a gotcha, right? In that it just blindly applies the function structurally and doesn't think at all about the mathematical correctness thereof.
So it's just like a map onto the two sides.
Right.
Okay.
Only it understands things like equations and inequalities and piecewise things and whatnot.
So my question, you were going to show me how you do the derivation of completing the square.
Okay, so yeah, so go back to multiply sides.
Yep.
And under applications, so you may need to open it up. Then.
Okay, here, let me copy it. Well, I can just.
Yeah, in fact, I think you copied it out already. And.
Well, I copied it from a different function, I thought.
Okay. Not. Well, you probably did, but it's probably pretty similar.
Okay, but at this point, you could get completely the wrong answer, right? And in fact, you are, in effect, getting, that could do just something completely bonkers.
Sure, although you have an equal sign, so it's fine, right? If two things are equal to each other, their principal square roots are equal to each other.
Yes, but not their square root defined more broadly and not the necessarily principal square root.
Right.
Yes, I mean.
So you'll. Right, so I only derive sort of the plus. The plus guy, and there's also, right.
So wait a minute, what are we doing here? So we're, all right, I guess my question is, if you wanted to represent, so we were just talking earlier today about find equational proof, okay?
Okay.
And it has these proof objects that it generates, so a verification function or a proof function, we're calling it. And the proof function has the property that when you, in the case of those proofs, you just apply it to nothing, it will go and verify the result. So my question would be, what is the analogous thing that you can do here? Is there some function that you could imagine generating in some mathematical setting, which is just an apply sides of a multiply sides of a this, of that, of the other? I mean, In other words, these functions are guaranteeing that they maintain the correctness of predicates. Is that true?
Except for the apply side. So if you want to prove something, that you cannot use apply sides.
Right. But for other proofs, what you would do is a proof, an algebraic proof would consist of, and how far can you get in algebraic proofs by just having nested apply sides, multiply sides, blah, blah, blah?
I don't think you can get there without using things like factor and cancel.
Okay. Which are meaning preserving functions. I mean, they're
right.
Okay, but so then what I'm asking is, what does a proof look like the show steps proofs of Wolfram alpha or something like this? What does a show steps proof look like as a sequence of apply sides, of a multiply sides, add sides, etc.? Do we know? I'm just trying to get a feeling for what we could use these functions for. In other words, is a proof a composition of these things?
Yes, I believe so. As long as we're restricted to the the 4 basic operations plus factor, expand, and cancel, then yes. Right. The moment you have to take square roots, you're in trouble.
Sure. But so for straight polynomial algebra, you're saying these should be enough. But then what I'm trying to understand is, what will be an example of something where in principle we could say, just like we have find equational proof, we could say find algebraic proof or something, and it would basically become some sequence of these kinds of operations. What would be an example of a thing you're proving that way?
That would be find the polynomial ring proof, right? We're in the ring of polynomials because,
yes.
Well, I guess.
So what's a thing? What's an example of something you could prove?
Over system of linear equations, step by step.
Yeah, system of linear equations. So
I see. Prove that x equals 3 given this system of linear equations.
Right. Yep. And I think I have an example of that somewhere. Maybe that's under scope rather than...
In terms of logical operators, does that mean that what that would look like is, what you're proving is blah, blah, blah set of equations implies x equals 3? Is that right? Or is that, what would be the actual representation of the thing you're proving?
Yes. So a bunch of equations in inequalities implies something.
Implies as in our Boolean operator implies?
Yes.
Huh. Okay.
Right.
Okay.
So if we, I think, here, let me find the examples. I can tell you where to look, but oh, maybe I have this under properties and relations.
Of what?
Right, so of multiply sides. Yeah, so like the second and third properties and relations. Right, so I have an equation x over 3 equals 5, and I can transform that to x equals 15.
Okay.
Right, and
but can you? You're using reduce here, and you're using solve here. Oh, I see.
Oh, he just showed that they give the same result.
Yeah, right. Okay.
Right, so basically you can combine enough multiply sides and divide sides and add sides to give you reduce-like simplifications, assuming you can get there with only those operations.
Okay, is it going to untangle conditional expressions and piecewise things correctly?
Yes, I mean, it knows how to handle conditional expressions.
Okay, so in other words, when it blows up as a bunch of conditionals, and then in the end, every path leads to the same result, that's going to work. Is that true?
Yes, it should.
Okay, that's cool. Okay, so the statement, given a certain setting for generate conditions and for assumptions, we should be able to make the statement, you'll never get the wrong answer just randomly using apply, add sides, multiply sides, etc. Is that a true statement?
Yes.
Right, with generate condition goes to true.
which you guys are planning to be the default.
And also, yeah, also the generate condition goes to piecewise, which is the default, is also giving the.
Yeah, I think we ended up calling that all. Generate conditions goes to all.
Okay, yeah. So
okay, fine. But so then the statement is you'll never get the wrong answer just using these functions.
Correct.
That's cool. That's very nice. What's the range of, you're saying over polynomials, you will never get the wrong answer, but I mean, it's not particularly useful doing this if you have square roots and things running around. Is that a true statement? That's
correct.
So for that, you have to use apply sides, which might give you the wrong answer if you do the wrong thing. Like if you do a square and apply sides, you might end up with something where, you've just proved 1 is equal to -1.
Yes.
Sure. I mean, you'd probably end up using a power expand in order to do that, like I do here. Yeah, so I'm sort of sneaking over the fact that I know that you can define square root in such a way that that power expand is always valid if you interpret it correctly.
This will already fail, right? Because this is, oh no, I'm totally confused. Isn't -x equals x, doesn't that evaluate? No, it doesn't evaluate. Okay, so I just proved, so there, I mean, that's a great example, which you could give in the documentation if you don't have it already, of apply sides giving the wrong answer.
There is an instance where it's correct.
I mean, it's not. I mean, it's not actually right. It's not wrong. It's just not equivalent to where you started out.
Well, wrong algebraically, except for x equals 0.
Right. No, it's not. It's not wrong. I mean, if -x is equal to x, then x squared is -x squared is equal to x squared.
Oh, fair enough. Yeah, okay, I understand. Because this expression, you're saying this is, for these other ones, like multiply sides and so on, the actual expression is supposed to be equivalent.
Right.
So it's a little bit confusing that apply sides has a name that sounds like multiply sides, but it has the property that it isn't equivalent.
Right.
Yucko yuck. Does that bother you enough that we should think about that some more?
I'm a bit conflicted. I think I mean, I documented this as a possible issue.
Mm-hmm. Okay, but so the typical, random person doing algebra. Actually, I'm curious. In a typical derivation that's done in sort of nth grade algebra or whatever, how, I guess the number of nested divide sides, multiply sides, etc., will be on the order of, I don't know, a few, 5 to 10 or something, perhaps. Is that right? I mean, that's the kind of length of our show steps derivations, I think.
Right.
I have a feeling for that. I mean,
I would say it's probably closer to 5 than to 10.
Okay.
But yes.
Okay. So, by the way, is there a I see, and typically there's a graph of what gets applied to what. So in other words, you have an expression, it has something done to it, that's like a node in a graph. Then you might have 2 expressions, and then you do a multiply. I mean, so sometimes okay, question, is there okay, so in some of these, like add sides, there is not a 1 argument form, right? The only 1 argument form that would make any sense. Is that right? Or add side? Go ahead.
So divide sides and subtract sides have a 1 arg form. Multiply sides and add sides do not. Because I'm not sure what that would do or be interesting for.
Explain to me in terms of the, ring theory or whatever, why that's different. In other words, go ahead.
Because it's natural to want. Well, I guess in terms of ring theory, there isn't that big of a difference, but right, it's natural to want to get the unit of the group operation, right? So for subtract sides, it produces a 0, and for divide sides, it produces a 1, right? So
Well,
basically,
you're
taking one side and you're applying the named operation to it to both sides, right? So you're subtracting one of the sides from both sides to get a 0 on one side. So it would be a little weird if add sides had a one argument form, because then you're going to be adding the negation of one side to both sides, and that just seems weird to me.
Adding the negation of one side to both sides in an attempt to get a 0.
Right. I mean, because I'm not sure what else the one arg form would do.
Well, I mean, I could imagine some bizarre curried form for one arg. I'm somewhat just thinking about what does it look like when you have one of these derivations that is essentially a functional composition of operations. Because it's kind of cool if what it looks like is, you know, if the actual derivation is something that basically says, with some appropriate, you know, multiply sides, if I'm getting the right composition operator, you know, add sides of 5, compose with divide sides. Does this make sense? Have I got the right composition operator?
I think so.
And that when applied to, you know, that becomes a derivation, basically. And that's an argument for having, you know, a curried form there, I suppose.
Right. But then I think you would want, right, but then I think it would be weird if add sides and multiply sides had curried forms, but divide sides and subtract sides do not.
Well, right now it's weird that multiply and divide, divide and subtract have one argument forms, and add and multiply do not have one argument forms.
I don't think it's that weird. I think it's, I mean, just like we have subtract and minus, which are, you know, one arg and two arg minus signs. But we don't have, you know, unary plus and binary plus.
Yeah.
You're right.
Does Adam or Roger have an opinion about this?
Well, I think you're using the curried form in a different sense. What you want to have the one argument thing to be the thing that you multiply by or add.
In that case, in that curried form, yes, which is kind of crazy.
Which is a different sense from what Itai has been.
No, I know. Itai's thing is to take the equation and try and just operate on that equation. Now, if the thing that's in there, so what does it do if the thing that's inside it isn't an equation?
Well, it depends on what it is.
Okay, so if it's add sides x, 6. Okay, fine. And by the way, it does all the right things with inequalities, right?
Right.
Yes.
I think this is rather nice. I mean, I think this notion of a thing like this that always guarantees to give the right answer is really pretty interesting.
Right. I mean, yes, I suppose, I mean.
Help me generalize. What are some other examples that we could imagine of operations like these, of guarantee to get the right answer operations on expressions? Or rather, operations on equations between expressions. I mean, in principle, yeah, I don't know. I mean, you know, applying monotonic functions to certain things will guarantee to get the right answer.
Yes.
It's kind of a more obscure case.
Well, monotonic and order preserving, so it's even more restricted.
Right, and applying function to an equation always gives the right.
Well, sure, to an equation, but not to an inequality.
But not to inequality, and to an inequality it becomes difficult. So you have to prove that it's monotonic. Okay,
but in a sort of symbolic world where we've got, yeah, I mean, okay, in the case of arbitrary axiomatic proofs, the analog of this is probably something where, you know, if you're, yeah, I mean, all these applications of axioms are more guaranteed to give, you know, if you have an axiom that says A equals B, and you effectively apply A to something and B to something, then you will guarantee to get.
Most of the case, like including the technology you use for that fine proof, equational proof.
Yep.
That uses an enlargement and rearrangement of the equations that you study. And so Grosvenor basis is very, you know, it's the same principle. You can say that that's it gets you that Grosvenor basis is the resulting equations that you need to be able to do reductions and have nothing go wrong. Do you see what I'm saying? It's like a Knuth Bendix
completion.
Yeah, it's a Knuth Bendix completion.
And how does that relate to what we're talking about here? I mean, in other words, is there a more complicated example of this, you know, add sides, multiply sides, that is essentially the Grosvenor basis thing?
I mean, there's similar things developed for groups. There's similar things for, you know, in commutative algebra, like the Grosvenor basis. There's similar things, but they usually don't terminate, except in some cases for non-commutative algebra and so on.
Right, but those are operations. In what sense? Okay, so here's a question. So if you wanted to derive for a given relation, you want to derive that sequence, the functional, you know, the functional composition sequence that leads you from one thing to another. What is there a method that is, I mean, that would be like, you know, solving, I don't know, some word problem for a group where you say, do this, 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 or it's like doing automated theorem proving that says, do, you know, go from here to here to here. I'm asking, in the world of things like Grosvenor bases and in the world of sort of algebraic computation, is there some well-defined, you know, existing operation that basically gives you that composition of equation transformation functions?
Yeah, I mean, LU decomposition, row reduction, Grosvenor basis, they're all instances of this.
Right. If you recall
right.
the steps.
Yeah, row reduce is clearly
yes.
Right? It's basically doing this only to rows instead of rows in the matrix instead of equations.
Yeah, and
so
LU decomposition is the same thing, you know.
Okay, but that's fine. But how do we represent those results?
You get the end result. Row reduce gives you the end result of it.
Right, so it does the transformations, but it doesn't show the transformations.
Okay, so were we to want to show the transformations, what would they look like?
They would be subtracting a multiple of one, because these represent basically linear equations. So you multiply one equation by some constant, you subtract two of them, and so on.
Right. So what that is, it would be a subtract sides. It will be a subtract sides. And notice that what we're doing in this case, it will be a subtract sides of a multiply sides. Well, actually, it's not multiply sides. It's one equation. Is it? What is it?
Well, you can see them as equations equal to 0, or, you know.
Yeah, right. So it will be a
wherever you feel like.
Right. So it will be a combination of subtract sides and multiply sides things that in this particular case happens to be applied to the matrix representation of the simultaneous equations.
And I can even give you an exact estimate how many of these, because that's the complexity of row reduction or LU decomposition. You know, we know that they go like n cubed or some such operations.
Yeah, that's interesting. Right. So in general, to solve an n by n system of simultaneous equations, you're saying that
for general equations, like even polynomial equations, that they'll be doubly exponential in the number of variables. I mean, there'll be many of them.
Oh, I guess that's why kids end up spending effort doing algebra, because these things have high complexity.
Right. But
humans still do that stuff.
I mean, sometimes there are shortcuts, and sometimes you're lucky, sometimes someone adapted a problem, so it's short.
Right. But I'm trying to understand, in terms of our add sides, multiply sides, and so on, what would be the analogous thing if we were just operating not on the equations, but on the coefficient list, effectively, right? Because that's what this is. That's, if I'm not mistaken. I mean, if I have a set of equations, I can, how do I go from the equations to...
so that's usually called a vector space, right? You can multiply a vector by a constant.
Right. So
you can subtract vectors and add vectors.
Right. So, right, when you have a square matrix, right, so then that really means M, the matrix M dotted with a pair of variables x, y equals, 0, 0. So it's two equations, right? So in this sense, I mean, I guess you could, right, so basically multiply, right, so you'd have the first equation, multiply it by whatever, I guess 1/3, and then add it to, another itself or another row,
right?
Which may be kind of trivial in the square case because the right-hand sides of the equations are all 0.
Okay, I guess the question that I'm trying to ask is, we've got these multiply sides things that operate on explicit equations represented symbolically.
Mm-hmm.
My question is, just for the sake of understanding how these things all fit together, were we to take those equations and represent them, if they're linear equations, just by matrices, right? What would be, are there functions that we could imagine that are the analog of multiply sides that are applied? What does multiply sides do when it's given a list?
Nothing, I think.
But does it?
Since this was intended for the elementary case, I think it does nothing.
Does it? Is it listable?
No, I don't think so. Oh, it is.
Actually, it is. Okay, which is reasonable. Okay, but the disembodied equations, which are only equations, we can't represent.
Right. So right. Well, also the point is, right, if you're going to do this for a matrix, say, then you need to be able to address individual rows or columns. Typically rows, but sometimes
I mean, you typically, often if you teach people to do that, you can sort of take things apart and do on individual equations. Otherwise, you use dot products and plus.
Yeah, right. By the way, someone on our live stream has asked, they want to know, given all the stuff we're doing here, what about symbolic linear algebra working with vectors and matrices as a whole?
It's coming, not now.
I know, it's a chestnut that has been roasting for a long time.
Well, there's more coming. So yeah.
Right.
But yes, we're aware of that. It's an important thing to address, and we'll have some pretty cool things coming there eventually.
Okay, but let's just reviewing multiply sides and all these things. I think you've convinced me that your generate conditions approach is correct and actually rather cool, even if there's a certain amount of explanation that's going to have to be given to people about these weird piecewise expressions that are coming out. The question of how much auto simplification should be done is not clear to me. And personally, I think, given that these are aimed at fairly elementary things, that we should try to auto-simplify when we can. Would you like to comment on that? I mean, we could always give an option for a post-processing option to determine whether we actually do that. But go ahead, what were you going to say?
What should be the goal of auto-simplification? Just simplify like thing, produce something small, or? So,
right. So what I personally would want is something that, and maybe this just has to do with the particular examples I've done, but I want something which actually does the multiplication through. So it's sort of like expand, but it doesn't go in and expand everything. It just expands the new thing.
Yeah, when you say multiply sides, you actually want the multiplication to be, you don't just want it to wrap the multiplicand around the whole thing.
Right. So
well, that seems reasonable. Is there a way we have to do that? I mean, that's
right. So if you look at the 1, 2, 3, the third scope example.
In what? So multiply sides?
Multiply sides, yes. So that's a case where I would have wanted to see 7b plus 7mx rather than
I
that.
completely agree.
Now,
I think
now
how do
you
we
could do
achieve
that
that?
with expand, but if you've already factored one side, you know, you don't want to completely expand it.
Okay,
So
well, how do we do this? Isn't there some kind of
Right, but for instance, if both of them were sums, do you really want to expand it out sums? So if it was instead of 7, there was a plus zx, you want it to expand it completely, or
what are you saying here? A plus bx here. Is that what you want?
what should happen then? You want it expanded?
No, I think what this did is fairly reasonable then.
Yeah, so maybe
Sigh.
yeah, I personally would not object to that being expanded, but yeah, I guess if it's a sort of, yeah, I guess you just how do you decide if it's a simple thing? But certainly,
okay. So my only real objection then is that expand doesn't go inside this piecewise. That I think is crazy.
it probably should. So I think we just never thought about it. So the only issue with this is, so if not the whole thing is piecewise, but it's piecewise inside an expression, should it still go inside or not?
You mean the expand?
Yeah, should expand still go inside something
Well,
like?
what does expand do if I say f of, you know, x plus 1 squared or something?
Nothing.
Say expand that, I think it'll do nothing, right?
Nothing, yeah.
Okay, so my statement would be, if the piecewise is, I mean, there's a certain set of structures. If it's look, if it's inside an
I
F,
think expand all go inside of piecewise?
Expand all goes inside everything.
Yeah. So right. So if you change that to expand all of %34.
you're wrong.
Nope.
It doesn't go inside piecewise, then that definitely is a bug.
Okay, but I think, okay, so the question is piecewise an algebraic-like operation? Give me what is a case where expand all has different behavior from expand?
Well, I guess the percent.
F of x plus 1, the one higher.
Yeah.
F of x plus 1 squared.
Okay, so this thing here, expand all, would go inside. What do we imagine? It's expand all is a very, very, very old function. What was it originally for?
I think it's, you know, for cases where you have like
square trigonometric functions and things like that. Yeah, it's square roots, right? Okay, fair enough. Boy,
it just doesn't go inside held arguments, and arguments of piecewise are technically held. So that's why it doesn't happen. So
right. By the way, what does multiply sides do in with logical combinations of equations? It should do the right thing, but it should do the right thing. It should go and apply to all of them. So if I say multiply sides of x equals 5 and y equals 2, multiply sides by 5, that surely should work.
Okay, so it should allow Boolean function with all arguments being equations and inequalities.
I think so. Why wouldn't it? And are there non-trivial things that happen there?
Well, I mean, for one thing, well, I guess you then have
subtract sides.
So the combining the conditions on this operation being correct for all the equations and inequalities may be complicated.
Well, that's good. Then we're adding value. I mean, what should that do? That should probably subtract sides from each part of that Boolean expression.
Okay, but so consider, you know, consider divide sides of A equals B.
Okay.
Okay, and now suppose we had, you know, divide sides of A equals B and something else.
Well, what is even going on here? I don't understand. Oh, okay, so wait a minute. If I see, so the first case there This is really a somewhat incomprehensible display of piecewise.
Why?
Can we do better? Because true is the default case, and it's like, what a weird thing. I mean, so the fact that we format, okay, question. If we weren't trying to be faithful to the internal representation of piecewise, how would we format a default case like this?
I mean, well, we might say otherwise. In fact, it might even do that in traditional form. Or maybe that's an alpha thing.
Oh yeah, I remember we did do that in alpha because this was really incomprehensible.
Right.
What happens if we do that? If we say solve that is a profoundly useless result. Okay. Well, I mean, it's useful as far as whatever. Okay. So that's another thing we probably should look at, is at least changing that traditional form.
Okay, that should be pretty easy.
To whatever it does in alpha, which I think we thought about quite carefully. Okay, but in any case, so the Boolean case,
one thing is the Boolean case, so it could only work if the right-hand side is not an equation, or if you have Boolean combinations in both the left-hand side and the right-hand side, or both arguments of multiple equations, then it's not quite sure what it should do.
I have no idea where to put this. I'm sure I've had some.
This originally started out as ILD, and then it came to me. And
do you have any idea where we stored it here?
Is there an? No, I don't know. Is there an ILD folder in there? It might be.
This is the ILD folder.
That is the ILD folder. Okay, then maybe. I think maybe under variables. I feel like it was like. No, that can't be right. I do not need to smith for that.
Oh well, okay. I'll store it under Algebra Calculus 01, and hopefully we'll move it later. Okay, all right. So, oh gosh, we're over time horribly here. I can't believe that these functions, which I thought were so simple, are actually quite non-trivial.
Right, I'm still not sold on the handling Boolean conditions, because then you're going to get Booleans of piecewise expressions. And
so what? I mean, what else would you get there? So in other words, somebody comes in, okay, so here's a question. I see, the piecewise expression is a Boolean if, no, it isn't. It's a
piecewise of equations, right?
So yeah, that piecewise is Boolean valued.
Right.
See what I'm saying? The values
right.
can be Boolean valued.
And also the piecewise itself is a bunch of implications, isn't it?
Yes.
Yes. Okay. But so what's the combination when we put in we put in a Boolean. My question is, as somebody tries to generate a derivation, do they end up with a situation in which they have a Boolean? They clearly end up with piecewises as part of their derivation. Do they end up with Booleans as part of their derivation for any reason?
Yes.
That thing, Stephen, if you take the value there, but below where your mouse was,
yep,
the Boolean piecewise, if you do, Adam, how do we get that to a Boolean fully?
Piecewise expand thing, right?
Give a method option to piecewise expand, which I don't remember exactly what it is right now. There is no easy way.
Okay.
Right.
That can be reduced to a single Boolean, Stephen. But they kind of you can see it like that can be expressed as a Boolean formula that says basically z greater than 0 and yz greater than that thing.
Yep.
Then you have to have the negation of your condition.
Yep.
Which is z less than or equal to 0.
Yeah, it's like constructing a CNF DNF type thing.
Kind of, because normal Boolean normal piecewise cares about orders. You have to include the negation of the previous clauses or conditions.
Yes. Okay. Fair enough. Okay. So what's your point? So your point is that I mean,
in principle, it is a Boolean, in this case.
Right. So okay. So then just to understand, there is a correct mathematical answer to multiply sides with a Boolean first argument. True or not true?
Yes.
That's a
If the
well-defined
second argument is not an equation.
Well, I don't know that it's that. I mean, I suppose I guess it would not be wrong to apply it to each individual thing in the inequality, but it's not obviously useful or interesting.
Okay, but it is useful or interesting if, as an intermediate stage, you get out those Boolean expressions, just like you might get out a list, and you want to not have to map into the, inside that thing. But let me make it more difficult. Okay, let's just say, just for the sake of argument, that we have something like, x plus y equals 9, or x minus y is less than 5.
Yeah.
Okay, is there anything sensible we can do with that?
I mean, you're branching.
That's not clear. What's the Boolean structure that should come out of it?
Well, okay, so what we want to be the case is these are meaning preserving things. So right now, I
don't know what it means to divide both sides by a Boolean valued thing.
What?
I don't know what it means to divide by x plus y equals 9 or x minus y less than 5.
I would think what it means is, I think there's you distribute over the or somehow. That is, if you've got a single thing and you're dividing it by blah or blah, does that not mean that you have thing divided by first blah or thing divided by second blah? Okay, what does it mean that the thing is meaning preserving? That is, it better be the case that if the equations were true,
yes, that the equation what it means is that if you reduce the input equation, or the input first argument by the output, if you reduce first argument is equivalent to output, you get true.
It's basically if everything in the input is true, then the output is true. So there is an implication going one way, and in the easier cases where we don't have the Boolean combinations, it's also clear what we should do, how we should derive things from the input. I mean, right. We can derive true from everything. So there is always some result that will preserve the implication. But what's the meaningful result for this? That it's not quite clear to me.
All right. So look, okay, let's not solve this here. Clearly what we put into 11.3 will be somewhat incomplete, but let's continue to think. I don't think the design is going to change.
Okay.
Do you agree? I mean, but we should think through what are all the cases we can deal with. I agree that there should be no auto expansion inside these things, but expand should do the right thing itself. I think in terms of the pure matrix case, that is, the how do we see the steps in a row reduce? I think this isn't, you can obviously, right. I mean, the derivation of steps is a different matter. That's more like a proof thing, and it's an interesting exercise for somebody to figure that out. It's a good. I will add it to my list of student projects. I think it's an interesting thing for somebody to do. But I don't think we need to. But you're telling me that in the world of like Grosvenor basis stuff and so on, that there isn't a pre-existing kind of, I mean, it is an algorithm, not some piece of, like the row reduction algorithm. What is the row reduction algorithm anyway? I mean, it's Gaussian elimination of some kind, yes?
It
Yes.
is exactly Gaussian elimination.
But is Gaussian elimination something for which there is a deterministic algorithm, or is it something,
Yes.
I mean,
Yes, there are many variants of it, but yes, it's deterministic.
but what I mean by that is, you know, when you do it by hand, you're kind of looking around for how can I add these two pieces so that I'll get a simple answer and so on.
But that's because you want to shortcut it, you know.
I see.
Yeah, I mean, you basically, the algorithm is you make the first one, 1, then you go to the second one, you make it 0, 1, and then you start canceling other, right? Well,
Right.
sorry, you make the
Okay,
first
fair
one
enough.
1, and then you can make all the subsequent entries in the first column 0, and then you go to the second, and so on and so forth, and you rearrange things if it's missing zeros or whatnot. So,
Fair enough. Okay, so question for these. So we haven't done knitting for these things, by the way, and also as a question of, are we going to leave these experimental, or are they going to be non-experimental, these functions?
I think it's sort of up to you.
I don't think they have to. I mean, if you feel like allowing the relation rel to be an inequality, a Boolean combination of relations is, if you feel that's really different, then
I
maybe.
don't think it's that different. No, I think it's just an extension.
Right. So then that's an extension we may not have in 2 days, but.
Right, but it's an easily addable extension.
Yes.
Okay, let us make them real. Do you really want to say add X there? Isn't that a bit confusing, just in terms of documentation?
As opposed to what?
Well, I don't know, as expr, for example.
I guess I just thought X was simpler for the intended audience, but if you think
what I'm worried about is X is itself a variable.
I see. Sure, I have no problem with changing that X to expr.
Okay, can you do that then?
Okay.
Okay, hold on, where was the other one? We've got one more of these guys. Apply sides, multiply sides, divide sides.
Subtract sides.
What's that?
Subtract.
Okay. Is there a guide page? There isn't a guide page for these guys, is there?
No, I don't think I put them on any yet.
Okay.
So that's.
Did you have back pointers to these guys from other stuff, like reduce and solve and so on?
I don't think I've done that, but it's easy enough to do.
Fair enough. We might want to do one quick look at the.
We always do knitting post these reviews, Stephen.
Fine.
So there's nothing
Fine.
surprising.
Okay, all right. Last moments here. Going back to the much more complicated story. Okay, I thought this was going to be like super easy.
Well, I mean, you will be comfortable with it soon enough.
Which thing?
No,
I wasn't thinking asymptotics would be. I thought that would be somewhat easy. I thought these add sides and so on would be like totally trivial 2-minute things.
I see. Yeah. Well, that's the thing of keeping track of conditions. Is not.
No, I know it's not easy. Okay, so just on the asymptotics business. So the main design thing that I'm a little bit confused by is, why do we have asymptotic integrate, asymptotic desolve value, and not asymptotic every other function that we're dealing with?
We will. We plan
Okay.
3 more.
Then I have another question. Like, with series, we don't have to have series integrate and so on right now, because integrate applied to a series does the right thing.
That's right.
So my question is, in this situation, is there an analogous kind of, I'm an approximate expression wrapper that we could use? Or do we have to have...
That's what I want to figure out. I want to release them experimentally now.
Fine.
And then we want to figure out whether we need to report on, there are different levels of reporting one can imagine, depending on follow-on use cases of the error term.
Yeah, and Stephen, I guess one reason we don't want that function right now is that in order to make it work, right? So if you're thinking of some sort of asymptotic expand with the first argument being d-sol value or integrate or whatever,
Yep.
we would need, that function would have to be hold first.
Yeah. Right.
And we don't want that.
But an alternative thing to do would be to say, to wrap the equation in some kind of asymptotic equation thing and say this whole equation is supposed to be true. I don't know, we could wrap a variable in that thing, something like that. I'm not sure. I mean, what we're asking for is not x of t, we're asking for the asymptotic x of t in some sense.
Right.
But there are a variety of other places we could put it. What concerns me is we don't really want to have, 50 functions that all have the asymptotic word in them.
No.
Unless the operation is really different.
Right. So I think that right, we don't want asymptotic Laplace transform or asymptotic inverse Laplace transform, but still we want asymptotic methods. So I think that we'll figure out a wrapper that we can use for that.
Fine. All right. Okay. So, and you were raising this question about, I'm still a little bit confused about the difference between the Booleans, which return true or false, and these other things which return expressions, and the fact that the specification, okay, so let's talk about that precision. In the case of numerical precision, it's a little bit weird because we will give a definite answer for a Boolean.
Yeah.
What do we do? What do we do?
Definitely true or definitely false.
Yeah, I understand, but what do we do? What do we do in this case? If we say n of 1/3, comma 10 greater than n of 1/3, comma 20. I don't understand that. So there are error bounds for both of those things.
Right up to the precision of the lower one, they're equal to each other. So one is not greater than the other.
So one of them lives inside. In this particular case, it lives inside, but could it not live in an overlapping but disjoint error region? Clearly, if I say interval 1, 2 greater than interval 0, 1, say greater than equal to, what is that doing? What is that doing?
Oh, it's okay. They only overlap at one point.
The first one is greater than or equal to every other number in the second one.
Oh, I see. Whereas in this case, it can't decide that.
Right.
But isn't that similar to the asymptotic less business? Am I being confused here?
If we had some serious object that would carry the precision, like what their order of approximation is, then it could factor into the asymptotic less and asymptotic equal, but we don't have it yet. Right, so
but could asymptotic less ever be confused in the same way that less is or greater or whatever is confused with intervals?
We can confuse. I can confuse pretty much any function.
No, I understand that, but generically, this is a case where the asymptotic thing is representing a function, right? Asymptotic less is about functions.
Yes.
Functions wiggle around all over the place.
That's right.
Right. And in particular, it's about the absolute values of those functions.
Yes.
Okay. But so my question is, are there cases like the case of this interval here where the answer to asymptotic less is it's not well defined?
Only if we have the imprecise functions. So it's if we have asymptotic approximations to functions rather than functions. If they are fixed functions, then no. So like with
if the graph of the two functions, intersects each other repeatedly, what is it greater than or is it not greater than?
It's not greater than. So greater than if it's not. So.
And what about it greater than equal?
Also not. So with function it's slightly different. So with numbers it's greater equal is the same, either greater or equal. In case of function, greater equal is not necessarily greater or equal. It may be greater equal. And then the negation of greater is not less equal in case of functions.
Humph. Is that going to cause us trouble? I mean, in other words, I see. So what you're saying is there is no way, I mean, that's actually an argument against the thing I was saying of having an asymptotic wrapper around an expression, because then every aspect of our inequality handling will no longer work for these asymptotic things. Am I making sense? In other words, if the things that are inside the greater, the less, and so on aren't ordered numbers, but are instead these functions.
So, I mean, I think one thing you need to keep in mind about the asymptotic orders is that they are partial orders. So, for example, if you do asymptotic less of sine of x, cosine of x as x goes to infinity, that'll give false. But also its negation of asymptotic greater equal.
Okay, so hold on, let me just understand this. So asymptotic less sine x cos x, x goes to infinity, is going to give false, right?
Yep.
And it's also the case that asymptotic greater equal of that is also false. I see, yes, I mean, that's obvious. Okay, I get it. Right. I mean, it's like we can think of this in terms of, yeah, okay.
We have many more of these partial orders coming for other domains. So.
Give me one example just for the hell of it.
We need ordered vector spaces for optimization.
Okay.
So, and in the case of ordered vector spaces, they can all be defined by what's a convex cone. And
yeah, I was seeing some of those things about cones. It's an awfully technical meaning of cone, isn't it?
No, we'll come back to that. It's
All
not
right,
for today.
right.
This is like a whole story there. It'll be very clean, nice.
Okay. All right. Well, listen. So, what's our conclusion here? Is our conclusion that we just put these in experimentally? I guess so.
I think we should.
Yes, I think that's a good idea.
It's pretty cool, Stephen. You know.
No, I agree. It's cool. You're missing an accent aigu on Monsieur Henri.
Oh, that doesn't exist in English. They don't have it.
What do you mean they don't have it? You've still put it in these places. Whatever.
Oh, you mean you import scripts from other languages?
Roger, usually when people write...
I'm kidding. I'm teasing you. Okay.
Okay.
We'll put it in. Okay.
It's okay. Great. All right. I mean, yeah, fair enough. Good. Okay, so is there any more that we need to review on this stuff other than some final knitting kinds of things?
We're gonna do the knitting now.
Okay.
So as always.
Sounds good. All right.
Okay.
Good stuff.
Thank you.
Thanks a lot. See you later.
Bye.
Bye. Bye.